Alrighty, we are back. We're looking at 3.8 implicit differentiation. And so let's take a look at explicit form and the derivative. We're on page 26 of chapter 3 packet. We're looking at 3.8. All right. So A, they have x, y equals 1. So explicit form would mean I just solved that for y. So y is equal to 1 over x, which I would do y is equal to x to the negative 1 power. And then when I took the derivative, it would just be negative 1x minus 2. And then I would rewrite that as y prime would equal negative 1 over x squared. All right. So we read implicit differentiation. All right. What about part B? They have x squared minus 3y cubed plus 5y. That's going to be a problem because explicit form, we can't do that. It can't be done. And so that means we can't do the derivative if we don't have it, as y equals. Right now, we will in a second. So we need implicit differentiation. Which is kind of a fancy talk for I can take the derivative of the variable that I want to focus on, and then I'm going to treat any other variable like how I treat a constant. All right. And so that's what's going on. But then I also have to add notation to it. And so this is kind of Leibniz was really good with developing this notation, like the dy dx stuff. So for example, we have, let's see, examples, d dx of x to the third. All right, and so that was just 3x squared. And we were just done. We just did the derivative with the power rule, and the variables agree. This has an x, that was an x, and so we just did the derivative. Part B, we have d dx of y cubed. Oh, now there's a problem because the variables are not the same. So see the x there is not the same as that. So they are not the same. The variables are not the same. And so what we do is we take the derivative like it was a y, like d dy, and so that would be 3y squared. But then you don't get to just do that because these don't match. What you have to do after then is we have to multiply that by dy dx. And so anytime you do a derivative of something where the variables don't match, you have to, throw that variable on the top dy and then leave the dx underneath. It doesn't just disappear like this did. When we did the derivative of that, it's just 3x squared, we're done. This, it adds another dy dx term onto it. So we must multiply by dy dx. All right, so what about if we have kind of one of each, and they have it written out, and so I'm not going to rewrite that. So we are doing the derivative. The way we read this, d dx, that first part, of x squared minus y squared is we are doing the derivative with respect to x. Derivative with respect to x. So what does that mean? They have d dx of x squared minus d dx of y cubed. And so what does that, how does that play out? Well, we do the derivative of this and they match, so it's just 2x minus, we do the derivative of that, that was a 3 though, I think. Yeah. We do the derivative of that, that's 3y squared, but then because the dx doesn't match with the y, we have to go dy dx after. And so we multiply that term. So now, if we take a look at the next one, we have to still apply the other rules that we have. So that was just add, so we just did the derivative of each and then we're done, that's it. But on letter D here, look at what we got going on there for letter D. They have d dx of x squared y cubed that's being multiplied. So that means we're going to have to use the product rule, right, with the first and the second. And so you could do, remember how that works, that is how do we always write that? The first times the derivative of the second plus the second times the derivative of the first, like that. So the first, we could do the derivative, or the first is just x squared, sorry. Then the second is y cubed. Well, yeah, you can take that and do 3y squared, but then you have to throw in dy dx. Plus, and then the second, y cubed, times the derivative of the first. That we could just take as 2x, and we don't have to put a little dy dx anywhere. And so that is how we do the derivatives. That's called implicit differentiation. We are still taking the derivative of it, but because they don't match, we have to add a little dy dx after it. All right? So we got to multiply. The variables that disagree get multiplied by dy dx. Okay, so let's do a couple of problems. Differentiate the following equations implicitly. And they only want us to do step one there. They identify 4 steps, but really it's kind of 2. They kind of went over the top with the steps here. So look, it says differentiate both sides of the equation with respect to x using the known derivative rules. And then it says collect all the dy dx terms on the one side of the equation, factor it out if you have to, and then solve it by using division. So really, that's just solving for dy dx at the end of the day. They only want us to do the first step for these. So we're only going to do step 1 out of our little 4-step problem here. We'll do the other steps on the next page, don't worry. So what are we going to do? We're going to take the derivative of each one of these. So d dx of x squared minus d dx of y squared equals d dx of 16. The derivative of any constant is 0. The derivative of that is 2x. The derivative of this is 2y, but because these don't match, we're going to throw in a dy dx. All right. And so it says differentiate the following equations implicitly, but we only want to do step 1 right now. So just step 1, that's all we did. for number 1. Step 2, 3, and 4 would basically, we'd move the 2x over there, we'd divide out the negative 2y, and then we have dy dx equals 0. We will be doing that on the next page. So I'm just trying to show you to get the hang of this. 2. So we have y cubed plus y squared minus 5y minus x squared equals negative 4. We're only going to do step 1, so just step 1. And so this is not d dx. I'm not going to write all the d dx's. We're going to streamline this a little. So we got 3y squared dy dx. We got 2y dy dx. Minus 5 dy dx. And then minus 2x, and then equals 0, because the derivative of constant is 0. All right. So if we followed all those other steps, we would have moved the 2x over, we would have factored out the dy dx, and we would have divided both sides by 3y squared plus 2y minus 5. And then that would be our answer for dy dx. All right. So let's look at the next page where they want us to solve this. So they want us to solve for dy dx on these. So page 27 here, we are going to do all the steps. All right, so we got 2 sine x cosine y equals 1. So step 1 is, again, this is my first, this is my second. And so let's do the first times the derivative of the second. So remember, sine, cosine, negative sine, negative cosine. So the derivative of cosine is negative sine. And that's a y. And then because I did the derivative of the y in terms of dy dx, or in terms of d dx, I have to add a dy dx to that. Plus the cosine of y, so the second times the derivative of the first, which is 2 cosine x, and then equals the derivative of 1, which is 0. So I can't multiply that. That's not cosine squared because that's cosine y, that's cosine x, and that's a 2. So there's just a 2 there. So let's see what we got here. We have 2, a negative, negative 2 sine x sine y dy dx plus 2 cosine x cosine y equals 0. So we're going to move this over and then divide by that. So and then divide both sides. And so we can simplify this dy dx. The negatives cancel, right? A negative divided by a negative is a positive. The 2's cancel, so you can get rid of those 2's. And then cosine x over sine x is really cotangent x. And cosine y over sine y is cotangent y. And so there we are, dy dx. Number, what are we on? 4. We got 2x squared y cubed plus 2x equals 4y. Okay. So again, we've got right, first and second, and the rest of them are single terms. So we have to do, let's see, write down the first, take the derivative of the second, and now because it's a y, we're going to throw in a dy dx. All right, plus, we're still on this term, we haven't done anything there yet. The second y cubed times the derivative of the first, which is just 4x. All right, and we don't need anything special because that was, x, and we did d dx. Plus, we do the derivative of that, that's just 2. And we do equals the derivative of that, that's just 4, but there's a dy dx on it. All right. So, yeah, now we want to get our little ducks in a row. So what does that mean? I want to isolate the dy dx's. So we'll move this over to that side. That multiplies out. So I'm going to subtract 6x squared y squared dy dx minus 6x squared y squared dy dx. All right, so that's gone. This is 4xy cubed plus 2 equals, now with that, right, factor out our dy dx, right, the opposite of the distributive property, and then divide both sides. And there we have our answer, 4xy cubed plus 2 over 4 minus 6x squared y squared is equal to dy dx. And let's double check that. Oh yeah, I should reduce it, right, by a factor of 2. I could factor 2 out of there, I could factor 2 out of there. So my final answer is 2xy cubed plus 1 over 2 minus 3x squared y squared. All right. Nothing but fun here. Okay, so let's take a look at number 5. And then when we get to number 6, we actually get to do that one 2 different ways. Oh boy. Alrighty-dighty, so here we go with number 5. We got xy to the 1/2 power, so do a quick rewrite, equals x minus 2y. And so we have the first and the second. So first times second plus second times derivative of first. Alrighty-dighty, so remember how this all works. First, we've got a chain rule thing going on here, so we've got to do the 1/2 xy inside to the negative 1/2, and then times the derivative of that, And so now I'm going to have to do this. So first x, derivative of second is 1, but then dy dx plus second y times the derivative of the first 1. And so that was the chain rule, because we did the 1/2 thing and the negative, right? Everybody on board? Yeah? Okay. And then equals, do the derivative of that, that's 1, minus the derivative of that, that's 2, but we need a dy dx on it. Oof, and now we're going to have to solve for dy dx. And that's going to be a little messy. So let's clean this up a little first. So this is 1 over 2 square roots of x, y. And that is times x dy dx plus y. And that still equals 1 minus 2 dy dx. Lovely. So now we're going to do the distributive property. So this is kind of like over 1, right? So we've got x over 2 square roots of x, y, dy dx, plus y over 2 square roots of x, y. And that equals still 1 minus 2 dy dx. Okay, so let's move this over here and that over there. Let's do a little switcheroo, shall we? So we have x over 2 square roots of x, y, dy dx. Plus 2 dy dx equals 1 minus y over 2 square roots of xy. Okie dokie artichoke. And now let's factor out the dy dx. And then we're left with x over 2 square roots of xy plus 2. And that's equal to 1 minus. So I think what we might want to do is get these all common denominator out. Like multiply top and bottom of this by 2 square roots of xy, 2 square roots of xy, and multiply this by 2 square roots of xy, 2 square roots of xy. This is a big mess. I think on the actual work I left it with the negative 1/2 and negative 1/2 and stuff like that. But oh well, too late. We're already spent here. So let's do it. So what do we have? We got 2 square roots of xy minus y over 2 square roots of xy. And here dy dx times x plus 4 square roots of xy over 2 square roots of xy. Over 2 square roots of xy. Okay, and now we multiply by the reciprocal of this, both sides. And so here we go, 2 square roots of xy there, and x plus 4 square roots of xy there. And the same thing here, we're multiplying both sides by that, square root of xy over x plus 4 square roots of xy. And so that cancels all off. And so there we are. Dy dx is equal to this lovely answer that goes, and I think that's it, 2 square roots of xy minus y over x plus 4 square roots of xy. What a mess! And I think that's what this would work out to be if I multiplied everything out and fixed the fraction. Multiply top and bottom by 2, that would get the 4, and then, yeah, fix that. Yeah, so there it is. On the paper, when I show the paper at the end, I left it in just -1/2 and 1/2, so for powers instead of the square roots. Oof. Either way, so the actual implicit differentiation wasn't bad. It's just anytime we derive the y, we had to throw in dy dx. All right. So that was just lovely. Let's look at 6. And 6 we can actually do in 2 different ways. And then we can show that the answers are the same. Oh boy. Won't that be fun? So let's take a look. 6. We could do explicit, which means I could solve this for y and then do the derivative. So let's do it that way first. Solve it for y. All right. And so that means I'm going to have to do the square root. Do I have to worry about the plus or minus here? Positive or negative? I don't think I have to worry about that. So we're just solving it for y, and now we're rewriting it. Do a quick rewrite. And now do the derivative. So chain rule, 1/2, leave the inside exactly the same, subtract 1, -1/2, and then multiply it by the derivative of what's in there, so -1. So y prime is equal to -1 over, right, -1 times 1 is -1, 2 is on the bottom, that goes down on the bottom as a square root. There. Let's do implicit differentiation. X plus y squared equals 1. So d dx of x plus d dx of y squared equals d dx of 1. So that is 1. That is 2y dy dx. This is 0. And so now we go ahead and move the 1 over to this side, -1. So 2y dy dx is equal to -1, and then we divide by 2y. So dy dx is equal to -1 over 2y. But again, if you solved that for y, like we did over here, we solved this for y, we could sub that in for this y. And if I put a square root of 1 minus x in there for the y, then we have the same answer. So implicit differentiation and explicit differentiation would be the same. All right. Okay, find the slope of the tangent line given that at 0.5, comma 0.2. Oh boy. So let's take a look at number 7 and 8 and 9. So 7 is, we got 4 minus x times y squared equals x to the third at 0.5, comma 0.2. And they want, find the slope of the tangent line. So first we got to do the derivative, then we got to put in the 0.5s and 0.2s. And that will give us the slope at that point, the instantaneous slope. Okie dokie. So let's do it. We got first, we got second. We got to do first times derivative of second plus second times derivative of first. So first, 4 minus x times 2y dy dx plus second y squared times derivative of first, -1. We don't need anything on that, equals 3x squared. We don't need anything on that. So what does this mean? We're going to, what are we going to do? Let's clean it up a little bit, do the distributive property here. So we have 8y minus 2xy dy dx minus y squared equals 3x squared. So let's move this over. So 8y minus 2xy equals 3x squared plus y squared. Oh, wait, I left off the dy dx. Careful when you're hurrying. Divide by 8y minus 2xy by 8y minus 2xy. So dy dx is equal to 3x squared plus y squared over 8y minus 2xy. Okay, and now we just sub in this for x and this for y. And that'll give us the instantaneous rate of change at 0.5. So 3 times 0.5 squared plus 0.2 squared over 8 times 0.2 minus 2 times 0.5 times 0.2. And when you type all that in and divide it out, you should end up with 0.56. So our instantaneous rate of change at the point, or the slope of the tangent line at the point, is 0.56. All right, for number 8, they want us to find the second derivative. So we got to do the first derivative and then take the derivative of that. So let's go ahead, show you what we have to do for that. find d2y over dx2 y squared minus 2x equals 3. So first, let's do the first derivative. We've got 2y dy dx minus 2 equals 0. And we add the 2 over, and we got 2y dy dx is equal to 2, and then we divide by 2y. And we got dy dx is equal to 1 over y, or y to the negative 1. Now, we want to do the derivative of that. So, if we're going to do the derivative of that, d2y dx2 is equal to negative 1y to the negative 2 dy dx. And then if I do a rewrite on that, we have negative 1 over y squared dy dx. But now we have a dy dx. So I wanna take this and put it in there. So I have my second derivative defined in terms of just y, negative 1 y squared times 1 over y. So d2y over dx2 is equal to negative 1 over y cubed. And there we have it. All right, find the second derivative using implicit differentiation. Oof, they want to end with a bang here. Let me cap those up. Do number 9. Because they must think it's just not fun enough unless you have to use that product rule again. So that's fine. We got the product rule down. We'll do it. So 1 minus xy, x minus y. That's the first, that's the second. First derivative second plus second derivative first. Okay, so we do the derivative of this, that's 0. So here, let's just do d dx of 1, d dx of xy equals d dx of x, d dx of y. All right, that's 0. That's derivative of, or the first times the derivative of the second, which is 1 times dy dx, plus the second times the derivative of the first equals 1 minus 1 dy dx. Okay, so lots of ones. Alrighty, so let's distribute the negative. So we got negative x dy dx minus y equals 1 minus dy dx. And now let's get this over there, that over there. So switcheroo here. Okie dokie artichoke. So factor out the dy dx. And then divide by, let's switch them around. Alrighty, and now we want to find the second derivative. So let's do the second derivative, d2y of dx2. And we got the high-low thing going, right? So high d low minus, no, wait, low, sorry. Oof, getting tired. Low d high minus high d low over low. Always starts with low and ends with low and over low squared. All right, so there's my h, there's my l. So low, 1 minus x times the derivative of high, which is 1 dy dx, minus high, which is y plus 1, times derivative of low, which is negative 1, over 1 minus x squared. Okay, and then just let's see what we got. 2y dx2. We got 1 minus x times dy dx plus y plus 1 over, because right, that times that is plus, over 1 minus x squared, quantity squared. And now we can sub in dy dx. We can take this and put it in right there. And so what do we end up with then? And so those go. And then we have y plus 1 plus y plus 1. So 2y plus 2 over 1 minus x squared is our second derivative. Whew. So it's just not fun unless you get to do both the product rule and the quotient rule on the same problem. What a lucky break. All right.